I knew we were saving it for some reason.
Nice. Yeah. Colleen and I rented canoes once, I guess about a year ago out there.
Kayaks.
Or kayak. We did kayak. So
yeah, that's the end thing. So my wife and I are dinosaurs, I guess, with our canoe out there.
yeah.
No, we should also learn to canoe. Yeah.
Kayaks are faster though.
Yeah, but it's a good skill. It's a different skill. Yeah.
You get two people in one canoe, so you can do pretty well that way. But in the short term, kayaks are fast.
So we will start because this is recording.
Okay.
So let me just say welcome everybody to this virtual seminar on equivariant borders and application. This is previous our event in BAM CMO next year. This is the first talk, and it's an honor to have here as speaker Professor Allan Edmonds from the Department of Indiana University, Bloomington, where he is Professor Emeritus. The title of the talk is Finite Group Actions on One Complex and Homology. If anyone has questions, please raise your hand, and I'll be glad to say it to Professor Edmonds, and just turn on the microphone and ask yourself. And thank you, Professor Edmonds. The time is yours.
Well, thank you very much. It's a pleasure to be here, and thank you for the invitation to share this little project. I expanded my title, as you can see. I had my official title there was in blue. I added the words playing at the top. That has been somehow my little COVID project to explore a fairly elementary topic of the sort I like most, when the questions are understandable to the person on the street, and one can look into them without worrying too much about what kind of machinery or other things one needs to use. And given the seminar topic in particular, I hope to say at least a couple of words toward the end about surfaces. Okay, let's see. Now I have to make there we go. So the question I have is how much about an action of a finite group on a one-dimensional CW complex acting by cellular homeomorphisms, permuting the cells, how much is determined by simply the action on homology. And one can break down this a little bit, and which representations could be realized as integral representations, how many distinct ways of realizing a given enumeration, how many distinct ways can one topologically realize a given algebraic representation? And maybe a more specific question was, how well does the representation on integral homology determine the fixed point set? Now, of course, these questions make sense in many, many different contexts, topological contexts, of manifolds, surfaces, four manifolds, n manifolds, spheres, and on and on. I'll be talking about group actions up to G homotopy equivalents in order to get a nicer answer. There's a certain thread of thinking about problems like this on one complexes from the point of view of graph theory, where the particular graph structure perhaps plays a greater role. But here I'm thinking up to equivariant homotopy theory. And what we'll see is we'll get really clean, simple answers, at least in the case of a finite cyclic group of prime order. So I'm going to start with a couple of pictures, and they'll, in fact, if you kind of grab onto the picture and have something to carry in your mind, a good part of what I had to say, you could just recreate from the picture. So looking at symmetries of a cube, and I've drawn a cube there, and I've got an axis of symmetry, that green dotted line. So I'm imagining a fourfold rotation around that line. No fixed point, so that's a fixed point free action on the one skeleton of the cube. If you try to think about it up to equivariant homotopy, you could try to sort of flatten it out and squeeze down. So I'm thinking that the top square is the red one on the right, and the four around the side are the blue ones, and the bottom square is no longer represented in that picture on the right. But you see the action rotating around. The outer square is it homologically as a consequence of the others. So we have this wedge of 5 circles with a free action of z mod 4. We could, if we're trying to draw a picture of it, we could even go further and take the quotient space. The big red circle gets down to a small red circle since it's covered 4 times, and the blue circle is covered trivially 4 times. And from that picture, you easily read off the representation on homology. There's one trivial one corresponding to the red, one trivial z corresponding to the red circle, and a group ring worth corresponding to the blue circle. Here's another symmetry of the cube. This time I've drawn the diagonal, the blue diagonal that goes between 2 opposite vertices. And imagine rotating that cube a 3-fold symmetry, which you see by looking closely at the vertex. It has those 2 vertices that are going in black, big bold. Those are the fixed points. And it rotates around somehow. And you're trying to simplify the picture so that you home in on exactly what's going on, let's say, on the representation on homology. So you can start collapsing, equivariantly collapsing some edges that are sort of superfluous from the point of view of algebraic topology. And I squeeze some stem down one way and squeeze everything else over to the other end. And I end up with this picture that to the right, which is shows the 2 fixed points. And then I've got 3 edges that run between the fixed points. Those are rotated among themselves. And then I have, so those are represented by paths that run between the 2 fixed points. And then what's left over, I have then, by the time I'm doing this collapsing, I have 3 circles that are permuted among themselves. And once again, we can pass to the quotient space if we like. We need to, when we're drawing these quotient spaces, we have the graph, of course, that we're drawing, or the one complex. We also need to find some way of labeling it. There isn't a completely solid way of doing it, but I've tried to label something that makes it indicate that those black dots are the fixed points, and the edges in this case are all trivial, or how shall I say, trivially covered. That's ambiguous there. Each is covered by 3 edges. So from this picture, one can read off the integral representation. It's a little bit harder this time, but that loop on the right, where you have an edge that starts at a vertex and comes back, that edge is trivially covered except for the endpoint. So are fixed. And so you see 3 circles cyclically permuted, and that gives you exactly the integral group ring of Z mod 3 in the first homology. On the other hand, if you look at the edge, the other generator of homology, what lives over that edge between the 2 fixed points, you see 3, but you're not getting the integral group ring anymore because there's a relation among those. And what you're actually getting is the augmentation ideal of the group ring in the end. So those are my favorite pictures, and we'll be elaborating on those processes that we did to arrive at them. So as a starting point for a general discussion, one convenient place to start is the observation. I'm sure it goes way back, but it's prominent in Sayre's book from the early 70s or maybe the late 60s, even, on groups acting on trees. Of course, the emphasis there is on infinite groups, but what about the finite groups? Every finite group acting on a tree has a fixed point. So that's the simple statement that people remember, that there's the group act, and it's easy to prove. But we can be a little bit more specific and say, in fact, not only is the fixed point set non-empty, the fixed point set, of course, is a tree. Well, you have to prove that the fixed point set's connected. That's what in this case. And then to go a little further from the point of view that I'm taking today, the action is actually G homotopy equivalent to a trivial action on a point. Now, I've drawn a picture here of a tree. That tree has some symmetry. You see the 2 red edges can be interchanged by a Z mod 2. The 3 blue edges down at the bottom could be permuted by a cyclic group acting order 3. Altogether, the symmetry group of this tree is Z mod 6. But if you look at it closely, the black stuff can't be moved, and the red and blue stuff can be equivariantly shrunk down toward the fixed point set. So if you shrink one of the red edges, you have to shrink the other red edge, no problem. Same with the blue edges. And then you get down to a tree with no action, with a trivial action, and then that's deforms to a point. So we'll be playing with that idea. So this is a kind of a general statement. I'm going to claim, I'm not going into much detail, and it's not in the direction of most of the rest of the talk. But one way you might generalize Sayre's little theorem is to say, what if you have a more general one complex with a group acting on it? So it has some homology, but suppose the action on homology is trivial. Of course, one way that might happen is to have a trivial action. And the claim is that's essentially what happens. So if you have a finite group acting homologically trivially on a connected finite one complex, then either the fixed point set is non-empty and the action is G homotopy equivalent to a trivial action, and X deformation retracts onto the fixed point set. And it's sort of an argument, sort of like what we just saw. But the way you get your hands on it is you think the homology is generated by simple loops in the one complex. And what can happen to a simple loop? Well, the group action moves that simple loop to another simple loop. But if it's actually a different simple loop, then that will be two different elements in homology. So it must be sending that simple loop into itself. And if you have too many simple loops like that, then that's enough to force the action to be trivial on those simple loops. Now, there is one catch that you have to trace through here. It's what if there isn't any fixed point set at all? Well, that simple loop could be invariant. And if there's just one simple loop, it can rotate on itself. And maybe you have stuff hanging off that's sort of trivial. But so in that case, the space is equivalent to a circle, and the action is equivalent to a rotation. One reason to mention this at the beginning, and without going into more detail, is that this allows us to think of our group actions as being faithful on homology. We understand what happens if you have a kernel on homology. So a slight elaboration of what I've said here is that if you have a kernel on homology, then you can pass to another space and another group, G mod the kernel, acting and have it be faithful on homology. Okay, so that's sort of generalities. Now we'll get down to more particular things. I tried to put this discussion in sort of a broad framework. Most of what I'm going to be doing here is in the top right of this thing here. G acts on X, and G has a representation on homology. I was meaning to get my little, let's see if I can do it here. I'm not sure. See if I can make my little, can't do it anymore. I practiced this once, but okay. But to put things in a bigger perspective, groups acting on one complexes is the same thing as groups act as homomorphisms into the outer automorphism of the free group. And it's the same thing as extensions of that finite group, with the subgroup being the free group. I put those double arrows back and forth to say how you can go from one to the other. The one of substance is Bruno Zimmermann and Mark Kuller's theorem that goes from a subgroup of the outer automorphism to producing an action on a space. The rest of that is sort of automatic.
So that's like a Nielsen realization for out FN.
You could say it. Yeah, that would be one way to say it. Of course, it makes use of some interesting things about splitting some of that geometric group theory basics about groups acting on trees and things like that. It's about when do groups split as free products with amalgamation or HNN extension. You need to know that the groups E that I've drawn here have that kind, they're infinite groups, and that they have that kind of a property that they have a splitting. You also see on the left-hand side of this diagram what happens if you want to think about group actions and specifying a fixed point. I'm taking the simpler approach of not worrying about what the fixed point set is. I will be saying there is a fixed point at some point, but I'm not going to worry too much about what it is. But if you have a fixed point, then your mapping into the outer automorphisms is actually going into the automorphisms, well defined at that level. And what that says on the level of group extensions is that the corresponding group extension you get in this kind of a situation has a splitting. So to go from the middle column to the left column, you have to produce a splitting, or say there exists a splitting, and then choose a splitting. And up at the top row, you say, well, there is a fixed point, then that means it comes from the other column. And if you want to say exactly what you're doing, you have to choose a fixed point. In all those cases, you have maps into the automorphisms of the homology group. That will be what I'm interested in following up on now. So we're going to talk about G homotopy classification of G actions on one complexes. Let's take the trivial case first. What's the homotopy classification of one complexes with no group action? Of course, everybody knows the answer. Finite connected one complex is homotopy equivalent to a wedge of circles. And the one way to prove that, I sometimes would say, well, take a maximal tree and collapse that to a point. And then what's left is this wedge of circles. A little more constructively, every time you have an edge with distinct endpoints, you can just collapse it to a point. And you keep doing that whenever you have an edge with distinct endpoints. And if you have no edges with distinct endpoints, you're left with a wedge of circles. So our question is, what's the equivariant version of that? And I just elaborate on what I was just saying about collapsing edges. If you have a group action on a one complex and you have an edge with distinct endpoints, you can't just collapse it, because then you have to collapse the whole orbit. And if the orbit has some homology, then when you collapse that whole orbit, you're changing the space, changing the homotopy type. So we look at a G reduction. We look at the edges such that each component of the orbit of that edge is acyclic, so it has no closed loops. Then you can form the quotient space. I put those braces in there. I'm not just going to collapse the orbit of the edge to a single point. I'll collapse each component of the orbit of the edge to a separate point. And then the group action will obviously proceed along there. With this in mind, we can always take any group action on a one complex and go through this reduction process, equivariantly reduction, until we get down to the point where there aren't any of those G collapsible edges. And if you think about when you get to that point, what you know something at least about the fixed point set. The fixed point set is a disjoint union of isolated vertices and wedges of circles. Because if you have an edge in the fixed point set that has distinct endpoints, you can collapse it, just like we did in the non-equivariant case. Another case where this tells you somewhat everything you need to know. If the action is free, then if you think about what this means, if you have an edge, it's being freely permitted, you can also collapse it and its orbit. And what that tells you, if you think it through, is that the orbit complex is then a wedge of circles. And we're talking about covering spaces here. So you have a covering space of one complex. So you can replace the quotient space by this wedge of circles and analyze it from that point of view. And we'll come back to that point a little later on. So I've formulated what I'm calling a normalization theorem. And this slide has a lot of words on it. We'll unwrap those words in the subsequent slide with some slides with some pictures. So I want to build on this reduction process that I just talked about. So the claim here is that if you have a finite group acting semi-freely on a finite one complex with a non-empty fixed point set, then the action is G homotopy equivalent to 1 in a certain normal form. And this rest of this slide will explain what normal form is. And the point is going to be that you can read off from the normal form everything that we might want to do, just like we did on those pictures at the beginning of the talk. The first point is the one we just talked about on the previous slide. Once you will do the G reduction process, then each component of the fixed point set is a bouquet of circles or a single point, allowing that the empty wedge of circles. After that, we have to do some things that require choices, and but we need to see that we can make the choices in a way that we can get down to a unique form. So here's what I'm going to say. And again, I'm going to draw a picture on the next slide. In the orbit complex, you have the vertices coming from the vertices all live in the fixed point set. And we have these different components. And of course, the overall space is connected. So that means that there are some edges that connect up these fixed point set components. Well, we can take a minimal connecting set of those. Those are principal edges now, because we have this is where we're using a semi-free action. In general, would have all different kinds of isotropy types, and that would be a situation where I really don't know too much what to say. In any case, at this second step, the fixed point set is included into a slightly larger space, so that if you think of each component of the fixed point set as a vertex, then you have a tree in the quotient space. Then, of course, over those edges that are connected, you have multiple edges.
So, sorry, Allan, can I interrupt? What does semi-free mean?
Means that a point is either fixed or freely permuted.
Okay, that's what I thought.
So no in between isotropy types.
Great.
And that's key here. That this is where we're using it. I think of this as sort of like handle sliding. If you had some tree, like maybe a triad there, that you're trying to turn into a straight tree, well, you can take one of these edges that connects between two different fixed points and slide it over. Because it's a principal edge, it can slide over a principal edge. And in that way, you can turn it into a linear tree. And then you can play around with some little lemmas about how you can, up to G homotopy type, change the order of the fixed point components in that tree to any order, in any order you want. And so I get that point in the second line of point number 2. I say, with the fixed point components in order, say, of increasing Betty number as you go from left to right. That's my choice. And then you have some remaining edges. By this idea of sliding the remaining edges equivariantly, or in the orbit space, just sliding them all down to one end. That'll be like a wedge of circles attached in one end. So let's look at the picture of what all of this looks like. I'm going to do the same deal with having some grayed out picture. So first of all, the fixed point set after doing the G reduction process is a disjoint union of wedges of circles. There I've got a wedge of 2 circles and a wedge of 2 circles and a single circle, and then a single fixed point without any circle on it, going from left to right, 2, 2, 1, 0 for the Betty numbers. The next step was we found those edges that connect the components of the fixed points. And I'm drawing it in the orbit space now in order to have less busy pictures, but you can draw the upstairs picture again, because this is symmetry actions. If whatever the group order is, each one of those blue edges is covered by that many copies of the blue edge, but with the endpoints all fixed. And then you do some sliding until you put them any desired order you want, but I propose decreasing Betty number from left to right. And then next, we have everything is left over among the principal edges that are freely permuted. Downstairs, each one of them is gives a single circle, and they're attached wherever, any place, but we can slide them down to one end and have them all be attached at one end at this point. So we attach them to the simplest fixed point set. So that's a picture you can carry around in your mind about what a normalized orbit diagram looks like. By the way, one of the interesting aspects of semi-free actions in this context is that my pictures and my diagrams are agnostic about what the group is. I don't tell you what the group is, but you take account of what the group is by when you build the total space of the group action upstairs as opposed to downstairs where we're drawing the picture. Over those colored edges, you have to have order of G copies of that edge, but the endpoints are pinned down and then they're permuted according to the group action. The possible orbit spaces that you draw, however, don't depend upon what the group is. It's sort of an ironic point, and wouldn't be true for more complicated actions of complicated groups. So let's think about some of the things we can say here. Two semi-free actions on finite connected one complexes with fixed points are G homotopy equivalent if and only if they have identical normal forms. From the normal form, you see the number and Betty numbers of the fixed point set. And those are obvious invariants of the group action. But the picture I'm drawing only depends on that information. And any group action can be turned into one like that by the operations I said. So we've captured everything up to G homotopy equivalence. Now we want to interpret what that means a little bit more. We can read off the representation on the first homology from that picture. There will be so many trivial z's, that's that z to the t, where t is the number of black circles in the diagram, the number of fixed point circles. Then there will be a number of copies of the augmentation ideal of the finite group G, one for each of those blue edges that connect two components of the fixed points set. And then you have what's left over. That's sort of the stabilization that in some sense you can almost ignore and just add on at the end. You have so many copies of the group ring corresponding to those circles at the end. So in this case, I have 5 fixed circles. That's a z to the 5. I have 3 connecting edges connecting the 4 components of the fixed point set. That gives me augmentation of ideal 3 times. And we have 2 red circles left over at the end, which then upstairs give me 2 copies of the group ring. We can, another way of saying this just in symbols, the 0th Betty number of the fixed point set is a plus 1. A is the number of edges between fixed point components. You have 1 more fixed point component. And B1 of the fixed point set is T, the number of trivial circles in that diagram. You can realize any representation of this general form by a semi-free action with a non-empty fixed point set. So I take z to the t plus I of g to the a plus z of g to the r, and I think of, well, let's say the most specific representation I need t circles, so let's put them all down there at the end. And I need some more fixed points to get up to a plus 1. So we add some isolated fixed points and put some blue edges between them. They'll be trivially covered. And then however much more group ring we have left over at the end, we add that many red circles at the end. And to build the action, of course, you take the total space represented by this quotient. As an example, any involution in SLNZ has this standard form. So many copies of Z, so many copies of the group ring of Z of cyclic group of order 2. And then what's the augmentation ideal in this case? That's the integers with the non-trivial involution on it. Yeah. So in that case, every representation of this sort is resolved explicitly. But of course, we see some ambiguity coming because I chose to put all the trivial circles over there at one end. But we know, in fact, that need not happen. So that gives us a nice way of counting the different representations. And this is what I had been mulling over when I first started thinking about all this, trying to sort through what was actually going on. Now, the number of equivalence classes of realizations of a particular representation of the form Z to the T plus I of G to the A plus Z of G to the R by a semi-free action with a non-empty fixed point set is, well, you just have to decide how you're going to parcel out those circles among the different components. Well, you have to partition T, the number of circles, into at most A plus 1 pieces. You might not put any circles on some of the fixed points, and otherwise you might put them all on one fixed point, or you might spread them out in some way. We don't care what order we put them in because we know we can change the order however we like. So this number, which you could write a computer program, trivial computer program, or actually it's probably built in. In fact, I think I checked, it's built into Sage, for example. But it counts them. Another way of saying this is this partition counts the number of lifts of a finite group in GLNZ to out of Fn. Being a subgroup of out of Fn is the same thing as a group action one-on-one complex. So we can find the different ones that give, of the ones that give semi-free actions by this count. You can do a similar calculation about based actions, and then you have the choice of where you put the base point. And it has to be a fixed point, and it doesn't matter if you have two fixed point components that have the same Betty number. It doesn't matter between those two, but otherwise it'll make, and you can count those. There are, by the way, in general, subgroups of GLNZ, or I don't know why I wrote that instead of SLNZ here, that don't necessarily lift, and that has to do with some subtle number theory related to ideal class group of the group ring, but that doesn't come up in the standard things we're looking at. I did leave out one thing here. Of course, a semi-free action might be free, and I was assuming you had a fixed point set. So I'm going to take a few minutes here to think about the case of free actions on one complexes for just a moment, and then we'll fold that back into the statement I was making before. So here's a theorem that goes back, it seems, in the literature maybe to Gaschitz from 1954. If you have a finite group acting freely on a finite connected one complex, then the representation on rational homology is completely given. One Q plus copies of the rational group ring R. That's quite a bit different than the integral version. Right? The group ring, the rational group ring actually splits as the augmentation ideal plus the trivial representation. And what really makes this go is that the rational group ring is semi-simple. It splits into simple pieces, and then you can think about the simple pieces. You think about those modules from a more modern language, modules of projective QG modules. And so using that, you can, it's a fairly easy calculation relating you relate the rational chain complex, which is pretty small, to the rational homology. You know, things like the jargon would be, you know, the Euler characteristic of the chain complex is the same as the Euler characteristic of the homology complex, and that's what essentially what makes it go. So there's nothing interesting from this point of view about what's going on in rational homology, except as an aside, I would mention that Farb and Hensel have actually looked at some issues, and this is a question I think that actually more originated in surface topology than in one complexes, but thinking about what they call the primitive homology of X, which is homology generated by closed curves that come from closed curves, closed loops, simple loops in the quotient space. And they actually find some interesting rational representation. I'm not following that. I'm not following that direction, but I want to think, what can we say about the representation on integral homology for a finite group acting freely on a one complex? Now that's what I'm trying to pin down. Well, if you're going to understand a free action of a finite group on a one complex, what you want to do is use covering space theory. You pass to the quotient space, then you have a regular covering space with group G, and that covering space is classified by a map of the fundamental group of the quotient onto the finite group G. In this case, the fundamental group of the quotient is a free group on, say, n letters, and we can describe that representation by a sequence of elements of G that generate the group. And just as an aside, I'm not following this up particularly today, the homology of X is given by the relation module abelionized. So this is a topic, this is a classical topic. People have looked a lot at this and wondered, I'm going to be turning the matter on its head a little bit. I'm trying to use this information to say something about the homology, about the action of homology. I think people probably have thought the more primitive thing to talk about is classifying these kinds of representations that determine covering maps up to what we call Nielsen equivalents and using homology to make the distinction. So we'll see how it goes. I'll just say a few words. You would be studying these homomorphisms up to what I call weak equivalence. That means you're allowing automorphisms of the domain and automorphisms of the range as well. So automorphisms of G. I don't want to have things that differ only by an automorphism of G. Automorphisms of the free group are determined or generated by Nielsen moves. I've sketched out a Nielsen move where you multiply one element by another element in the sequence in a basis, or you invert an element. And so you can look at these sequences of elements of the group G and apply these moves and see if you can somehow or other turn your sequence into something very particular in the same way that I did when I was drawing those diagrams. So people who've studied this have found cases where you can prove that any two generating n-tuples for that group are weakly equivalent. On the other hand, they have found a few examples of generating n-tuples that are not weakly equivalent to one another. And basically they do it by saying something about what's happening on homology. But one case where we can say that there's a unique such representation in this sense of covering space theory is when you have a finite abelian group. So this is sort of interesting to me. I knew this all along, just on my own for cyclic groups. And then, so if you have a cyclic group, you can think of a representation that just maps one generator of the free group to a generator of the cyclic group and all the other generators trivially. And you can use Nielsen moves to get to that sort of a situation. If you have an abelian group, you use the structured theorem for finite abelian groups, and you sort of make the first one generator go there, and then next and next in a way. And if you were, some of the literature is a little hard for me to read because they're not allowing for these automorphisms of the group G. And so then you end up with a kind of a complicated count. But if you are willing to always apply automorphisms to group G, in fact, you get down to essentially a unique such thing. But in particular, for my purposes today, for a finite cyclic group acting on freely on a finite connected one complex, then the representation on homology is of the form 1Z plus copies of the group ring. And that's exactly what we saw way back at the beginning of the talk when we had Z mod 4 acting freely on a one complex. And it's exactly the same picture. You'll have one circle that is covered, cyclically covered, and then you'll have the other circles that are covered trivially. And of course, when I say it that way, it's completely clear that any such representation of homology is of the form Z plus Z of G to the R, and any such representation can be realized. One thing that bothered me a little bit about this was that, well, what about other groups? And I say, now I've made a misstatement in my, I found out the statement. I'm saying, suppose you have any finite group acting freely on a finite one complex, so get rid of that cyclic group there. I didn't mean that. For any finite group acting freely on a finite one complex with standard representation, Z plus Z of G to the R, then in fact the group is cyclic. So it's an interesting little exercise. I haven't seen it stated this way, but by looking at the action on homology and the chain complex that you get there, you can build a complex which is eventually a periodic chain complex. And then you end up seeing that this group has to be a finite group of periodic cohomology of period 2. That's the line of reasoning. I'm not going to write out anything. This is just an observation for our purposes today. Okay, let's bring that observation back into our discussion of actions, of semi-free actions. If you have a group G is a cyclic group of prime order, which is what I'm going to talk about now, then it's automatic, the actions are automatically semi-free. We can calculate explicitly the number of ways that such a group acts on a finite one complex up to G homotopy. We start out by writing the Betty number as a sum of P's and P minus ones and T for whatever's left over. For each such triple, you have a representation, Z to the T plus augmentation to the A plus regular representation to the R. And we can realize any such representation in exactly this partitions of T into at most A plus 1 pieces according to how the fixed point set is split up. What if there aren't any fixed points? Well, if n is congruent to 1 mod P, there is one additional free action that comes up with that representation, that kind of a representation, Z plus Z of CP to the R. And there we'll have a free action. So there's one more possible free action if the numbers all align perfectly. So that's my takeaway for you have a picture of these actions and you can count them completely, including the case where there aren't any fixed points at all. Okay, let me just say just a few words about some analogs on the case of surfaces. I won't have anything too much of substance, but just to put this into context, there is a version of Gashuitz's theorem for finite groups acting on surfaces. One can attribute it to Chernve, or you can just wave your hands and give a similar proof to what I talked about looking at the equivariant chain complex. The first homology of a surface with a group action is 2 copies of the trivial representation plus copies of the regular representation if you work over the rational numbers. We can think about what happens if you have a finite cyclic group, and those of us who've looked at finite cyclic groups acting freely on surfaces have a picture of what those look like. They're pretty trivial. You have a torus with an action on it and a bunch of stuff trivially covered, and you see exactly 2 copies of Z plus Z of G to the R. And it's a question I'm putting out there with don't have too much of an answer for it, or don't have any answer for it, is what are the integral representations that might come up in this situation? Some algebraists are somewhat interested in this kind of a question. From my point of view, one possible conjecture would be that if you have a non-cyclic group acting freely on a closed orthogonal surface, then the first homology has the simplest possible form over the integers if and only if G is abelian of rank 2 and the action is not freely Borden. This would be the case where the action is essentially a free action on a torus, rotating the 2 different factors of the torus together with some trivially permuted higher genus surfaces. That can occur for that kind of a group acting. I suppose it's probably the only way. Finally, we might say, what about non-cyclic groups? Just get your hands on an interesting representation somehow or other. And perhaps one should think about, of course, one should think more closely about the symplectic structure that has to be preserved by the group acting on the surface. Finally, just a couple of questions back on the one complex stage. I have this really basic representation on homology, Z to the T, I of G to the A, Z of G to the R. If I don't assume I'm looking at semi-free actions, is this enough to say that the group action is homotopy equivalent to a semi-free action? I think it might be. I know a few cases that like if it's just group rings and the group is solvable, I can prove that, but it's a little bit slippery otherwise. A weaker question would be, if you have this representation and the representation seems to be predicting that it should have a global fixed point, is it true that it has a global fixed point? That would be true if it were a semi-free action, of course, or a homotopy equivalent to a semi-free action. The representation on homology tells you the Leschetz number for all the non-trivial elements, actually, by playing with this algebra. And if you assume those are non-zero, then the Leschetz fixed point theorem tells you that every element has a fixed point, but at least in the abstract, that's not enough to show that an entire group has a fixed point. And certainly in higher dimensions, things can go quite haywire. That's a good place to stop. Thank you. I've enjoyed talking with you.
Thank you very much, Professor Edmonds. Yeah, really so interesting project. Yeah. So we can start with questions, comments. Just raise your hand or just turn on your microphone.
I guess I have a question. So when you identify this for these semi-free actions, we have this kind of trivial piece, at least for the cyclic groups. There's the trivial piece. Well, I guess the group each contribution of the group ring gives a trivial representation, but which each of those is kind of coming from like the sum of the cycles, right? The inside that piece of the homology. All of those are really short in some sense, right? And then but there's the one other copy you said of the trivial representation. And that one, my intuition is that one's really long. I guess that one should be as long as the group is big.
Yeah. I sort of drew that picture at the beginning in that with that in mind. Yes.
Okay. Yeah. So I guess I'm asking if that intuition more or less carries through in general. Yeah.
I think that's exactly what the picture would look like for a cyclic group. Yeah.
Cool.
Another question?
I have a question, Professor Edmonds.
Mm-hmm.
But I'm afraid it's not a question of what you said about perhaps what you didn't say. Eric himself made a very nice proof when he studied surfaces with free actions, on which of these surfaces could be filled in, but with an action that is not necessarily free.
Right.
Okay. So whenever you take one of these cases, then there is some sort of core or fixed point data that is in the filling.
Right.
In the 3-dimensional, you can have fixed points.
Right.
Well, this is one of your objects. It's one skeleton, and it has an action of the group, and it satisfies all the conditions that you have.
Mm-hmm.
But I was then thinking, what type of actions can one have of the group that we have on top? So which type of diagrams are possible as fillers?
Mm-hmm.
And I was just thinking if any or not any, or of course there are a lot of conditions, but I was, especially when the groups are the Platonic groups,
Right.
Which types of possible cores can one get?
Right.
So that's why it's a question on things that you didn't say, but
Right. Yeah.
But if you have considered exactly this case in which you fill the surface, but not with a free action.
Right. Exactly. I understand what you're saying. And you're saying that in general, that core has an action on it.
Exactly, and it's one of the exactly things that you studied.
Right. Yeah. Exactly.
I don't see any reason it has to be semi-free though.
No, it doesn't have to be. No. But it's somehow one of these things that Edmond was saying, and I was wondering, one can classify them also, like say, this is the only thing you may have, which would be like the opposite question would be, you give me one of these one-dimensional complexes with an action, can you make it thick? Can you thicken it in an intelligent way that it gives you something interesting?
Right. Yeah. So there you do have some issues, don't you? Because when I say the one complex, I'm not worrying about the filling, and if you have an isotropy group that is at a vertex that won't act on 3-dimensional space.
Exactly. So we have to restrict ourselves to finite groups of SO3 or something like that.
Exactly. Yeah. So all isotropies. So we're talking about one complexes with group actions where all the isotropic groups at vertices are subgroups of SO3.
And then the question is, could I thicken it in an
Right.
And I was wondering if there's some obstruction in homology on the groups that you mentioned precisely.
That's interesting. Actually, there is some literature on the question of, having a group action on a CW complex and then embedding it into a linear representation of some high order, like the Whitney embedding theorem with a group, right? And, we're talking about the lowest dimensional case of that. And loosely speaking, I think the obvious dimension restrictions. So if you have a one complex going into 3 space, that sounds okay. And then your local representations should all embed okay.
Exactly. So then one can perhaps build up some sort of obstruction condition to do it. Nice. But in those cases, Professor Edmonds, whenever you also consider general action, not just semi-free, it becomes wild.
Yeah. Yeah,
or it's up
for example, and I haven't really pursued this, I probably don't have the energy. You might, as a first next step, I tried for a while to think about what happens if you have three isotropy groups, that you have fixed points and freely permuted orbits, and then one other isotropy group that's in between. And I got stuck fairly quickly on possibilities. Among other things, you can start to draw, you can draw orbit diagrams in exactly the same way. You had to label them E, H, and G, let us say, but for all the edges. But then just because you draw a picture doesn't mean you can realize it. So we're back to sort of your question there. Or maybe the realization isn't even that well defined up to equivariant homotopy, how the pieces relate to one another. So
it's a very difficult thing.
I think it's combinatorially pretty difficult. In the case of three isotropy groups, you might be able to say something, but it was becoming unpleasant to think about it at the time I did, and I haven't gone back to it.
What about the case of simple groups? I know this is very far, like I have in mind 5 or something, but it is having no normal subgroups, would that somehow make the analysis more easy? I'm not sure.
Yeah. Well, it would lead to at least your representations on homology would then automatically be faithful.
Sure, yeah.
But otherwise, I don't know.
Professor Edmonds, and do you have evidence for this conjecture that you write in the previous slides? Yeah.
No, just that, in the sense of that's what I can see, right?
Because for me it's quite similar when we have free actions of abelian groups, and we can put and we can reduce everything to just the disjunct union of torus. So
right, yeah,
it's not like that direction that we are thinking about.
Right. Yeah. If I reduce to an action on a torus together with other stuff being added on equivariantly, as long as that other stuff doesn't interact very much, so that's why it would work in the case that I was looking at. But
and do you have any calculation with elementary two abelian groups? Yeah.
No.
We can talk about some quite irreducibility of the representation.
Yeah, no, not really.
And again, something that you didn't say, but it somehow brings me also the attention that one can somehow also put some sort of labels into the points, like representations on, like thinking on K-theory or thinking on Breton homology.
Right.
Would it make it very complicated? It's also semi-free somehow. I have a fixed point, but now I have several types of representations.
Let's see. I'm not sure how you're still saying, you're assuming it's semi-free.
Yeah, I'm assuming now that you also have a vector bundle over it, and you have an action. But let's forget about those things, and then I just do the spectral sequence, and I localize on points, and I not only have an orbit type, I have a representation.
Right. Yeah.
Of a fixed dimension, let's say. I don't know.
Yeah.
And so I would like to do the same classification.
Right.
Instead of just orbit types, it sounds that one could somehow use your approach to somehow glue these things. Because there would be some sort of Breton homology, as they call it. You put some labels into the orbit types.
Right. I haven't tried to think in that direction, but it makes sense.
Very nice, very nice. But anyway, very, very Professor Edmonds, thank you very much. I liked your talk.
My pleasure.
Thanks, Allan.
Nice to see everybody.
So if there are no other questions, so we end the session, and thank you to Professor Edmonds. Yeah, it was a pleasure to hear you.
Very nice.
Very nice.
Thank you very much, Professor Edmonds. Thank you very much. Very nice talk.
Thanks a lot.